Welcome back, everybody. We're continuing our look at electric fields. This video we're going to look at how we can calculate the strength of the electric field at a point in space surrounding a point charge. Okay, so here's our key knowledge focus. Basically, we're going to look at this equation here for the most part. Okay, that's the equation we use to calculate the strength of the electric field. And we're just going to remind you guys about using an inverse square law, okay, just like we did with the gravitational field. All right, so let's just get straight to it. Okay, so the electric field strength, which we give the symbol capital E, and we're talking about the electric field for point charges, okay, so protons or electrons, or some kind of small object that has a positive or negative charge that we can pretend is at a single point in space. Okay, it's not spread out, it doesn't really have a size, we're just talking about a point. Okay, and this point happens to have a charge, that's a point charge. Okay, so the electric field for a point charge is given by this equation here in red. Okay, so E is the electric field strength, we give it the units of newtons per coulomb. Okay, so you can consider the electric field as being a force per unit charge, just like the gravitational field is a force per unit mass. Okay, so for every coulomb of charge, then the charge will experience a force based on the value of the electric field strength. Okay, we'll touch on that later. This value here, K, this is a constant. Okay, we can call it Coulomb's constant, or the electric field constant. Okay, I don't think it's actually called the Coulomb constant, but we'll call it that just for giving it a name. It has a value of 8.99 times 10 to the 9. Okay, quite a big value. Don't worry too much about the units. The units are just there to make it work, to make this equation work. But you probably want to remember that. You want to commit that number to memory. Okay, so 8.99 times 10 to the 9. That's the value that you'll be given in your data booklet when you do the exam. Some questions, though, will tell you to use a value of 9.0 times 10 to the 9. Okay, so just remember when you're doing questions in an exam, the values given to you in a question always trump the values given in the data booklet. Okay, so they override. But for the most part, you'll be using 8.99. So just remember that number. Okay. Q in the numerator of your fraction, that is the charge of the object exerting the field. Okay. So just like masses exert a gravitational field around them, the charge exerts an electric field around it. Okay. So Q is the value of the charge that is exerting the field, not the value of a charge that is in the field. Okay. And R is the distance from that point charge in meters. All right. Now, you might look at this and say, hey, that's very similar to something that I've seen before, and you'll be correct. Okay, that is actually very similar to the gravitational field strength equation. Okay, so that's your gravitational field strength equation. They look pretty much exactly the same, just the values are different. Okay, just remember, that's what it looks like. Okay, it's not a crazy formula to remember if you remember the gravitational field formula. Okay, again, that'll be given in your data booklet somewhere. All right. Okay, and just also very important, we're talking about a point charge. Okay, so there's no center of charge or center of mass that we have to worry about. The charge is a point in space. Okay, it doesn't have a physical size. It might have a physical size in a question. Very rarely will you get something like that. Mainly, most of the time, it'll just be a point in space that we're talking about. Okay, cool. So that's your equation. All right. So the units of electric field strength. Okay, newtons per coulomb. Okay, that seems to suggest that it is a force per unit charge. Okay, just like the gravitational field is a force per unit mass. Okay, so what that means is, if there is an electric field strength of, say, 1.2 newtons per coulomb, that means if you put a charge of 1 coulomb in that field, then that charge will experience 1.2 newtons of force. Okay, because it's 1.2 newtons for every coulomb of charge that your object has. All right, so a 2 coulomb object will experience 2 times 1.2 or 2.4 newtons. Okay, and so on and so on. All right, again, that seems to suggest that there's a relationship between the force and the charge and the electric field strength, and that can be summed up in this equation here. Okay, the force that a charge experiences is equal to the size of the charge, Q, multiplied by the electric field strength that the charge is in. Okay, so just remember that formula. That's also very similar to gravitational force being equal to mass times gravitational field strength. Okay, and you'll see there's a lot of parallels between gravitational field and electric field as we go through the notes. Okay, so just remember that that's what the field is. Okay, it's a force per unit charge. Cool. All right, let's do a question. So we've got electric field strength. Calculate the electric field strength at a distance of 50 centimeters to the point, to the left of a point charge of -3 times 10 to the -6 coulombs. Okay, so what does that look like? Well, here's your negative charge, 50 centimeters to the left, somewhere over here. Okay, 0.5 meters. That's it. Okay, what is the field strength at that point? Well, now we know how to calculate the field strength. It is just E equals K times Q over R squared. All right, put all your values in. 8.99 times 10 to the 9 times the charge, which is 3 times 10 to the -6, divided by the distance in meters, 0.5, and remember to square it. Okay, that is very important. And in doing so, we get something around 107,880 newtons per coulomb. Okay, quite a large number. Okay, but you got to remember that charges are actually very small values. So if you were to put a charge in the field at that point, okay, the force that it would experience would probably be on the order of 1 or 2 newtons, because the charge itself is very small. Okay, so the field strength might be pretty big, but the charges that are being placed in the field are generally quite small. So the forces tend to be a normal size. If you want to do significant figures, let's do 2 significant figures. 1.1 times 10 to the 5 newtons per coulomb. Cool, very straightforward. Just apply the equation, okay? Just remember to square your distance. Very important. The negative value, okay, if you were to include a negative here, okay, you'd get a negative answer. That negative sign will just indicate that the field is pointing towards the charge that is exerting the field. Okay, so if you want to give a direction, you say that the field has this magnitude and its direction is to the right in this particular example, okay? Because if we're to the left of a negative charge, the field is going to point towards the charge, which is to the right. Cool, that's it. Okay, just apply the equation, nothing more than that. All right, question 3. So we've got 3 point charges with equal magnitude but different signs, shown below. What is the direction, if any, of the electric field at the point marked X? Okay, so here's X. What is the direction of the field at that point? There was a very, very similar question, I believe, in the 2017 exam. Might be 2018. I think it's 2017. I think it was the very first question in the short answer. Very, very similar, something like this. Okay. So how do you do something like that? Well, you've got to remember, the electric field is a vector. Okay. So if you have multiple charges exerting the field out into the space around them, then to calculate or to figure out the direction of a field at a single point, you need to consider the field from all 3 charges as vectors and then add the vectors together like you would with, say, forces. Okay, so let's draw the field as a vector using some arrows from each of the 3 charges at that point marked X. Okay, so for this positive charge on the left, we know that the field points away from positive charges. So the field from this positive charge is going to be pointing to the left like that. Okay. The field due to this negative charge in the middle Well, you've got to remember that the field points towards negative charges. So, and if the charges are the same magnitude, and this point x is exactly halfway between this positive and negative charge, then the magnitude, the size of the arrow, is going to be the same as the one from the positive charge. So that's also going to be pointing that way. All right. Finally, we've got this positive charge all the way here on the right. Okay, it's further away than the other two charges, so the field is going to be weaker. All right, which direction will the field be pointing from this positive charge? Well, fields point away from positive charges. So you say that the field is going to be pointing that way, something like that. Okay, smaller arrow than the other two because it's further away, the field is weaker. What do you get when you add these arrows together as vectors? Well, you've got one arrow pointing that way, plus another arrow pointing that way, minus the arrow pointing the other way. So overall, the arrow that you end up getting is like that. Okay? So overall, the direction of the field at that point is to the right. Okay? So that's how you add fields together. You have to consider them as vectors and then add the vectors together in whatever way that you think is necessary. In this case, it's just necessary to consider the arrows and the directions that the arrows are pointing. Don't actually have to work out magnitude. However, as a bonus problem, I'm not going to go through it here. If you want, if each charge has a magnitude of q, derive an expression for the field strength at this point marked x. Okay, based on the values that are given here in the picture. All right, that's a bonus problem for you. All right, cool. So we've got this inverse square proportionality again, just like we did with gravitational fields. Okay, so the electric field we can say is proportional to this 1 on r squared value. Okay, so that means basically if you double the distance, your field strength decreases to 1/4 of its original. If you triple the distance, your field strength decreases to, well, 3 squared is 9, so 1/9 of its original value. Okay, if you halve the distance, half squared is 1/4, and so 1 over 1/4, 1 divided by 1/4 is 4. So you get 4 times as strong. All right, and that's all summed up here in this paragraph down here. Okay, so just remember that your field is based on an inverse square proportionality, just like your gravitational field. Okay, so just keep that in the back of your mind. It'll help you give some ballpark answers when you're doing some questions, okay, just to make sure that your answers are sort of on the right track. All right, and just remember when you're doing calculations to square that distance in your calculator. Okay, that's the most common mistake. People forget to put a square when they're typing it in on a calculator, and then the answer gets stuffed up. Okay, so just remember that. Okay, inverse square proportionality. So here's a question. We've got field strength at a distance r from a point charge q is 4 newtons per coulomb. If the charge is tripled and the distance is doubled, what is the new field strength? Okay, so the way that I would tackle a question like this is I would say, all right, what's the old field strength in terms of these values? Well, we know the electric field is simply just equal to k times q on r squared. Okay, we don't know what q is, we don't know what r is. Don't worry about that, okay? We know how they're changing though, okay? So the new field strength can be written as k times, okay? So instead of q, we've now tripled the charge. So instead of q, it's going to be 3q. And the distance has doubled, so instead of r, it's going to be 2r. Just remember to put that 2r in brackets, because what you're doing is you're replacing the r with the 2r, okay? Now if you expand this out, you end up getting something like k times 3q on 4r squared. And what we can do is we can take this 3 on 4 and separate it out from the rest of the expression. So we can write it as 3 on 4 times kq on r squared. Now we know that kq on r squared, that's just the old field strength. Okay, so our new field strength is 3/4 of the old field strength. The old field strength was 4 newtons per coulomb. So 3/4 of 4 is just 3. newtons per coulomb. Okay, so that's how I would tackle a question like this. Try and represent your old field strength just in terms of the equation for field strength, and then find your new field strength in terms of the old field strength, okay, by this process here where you replace your values with whatever they are. Then you try and separate out that fraction to see what fraction of your old field strength your new field strength is going to be. Okay, you can do the same thing for force when you have a force question, because the formula is pretty much the same thing. Okay, all right, so that's it for now. So we've learned how to calculate the strength of an electric field at a certain distance from a point charge. Okay, very, very basic equation. Next time we'll start looking at how we can calculate electric forces. Okay, so I'll see you then.